The next model is called an Inception model, right? So this is a research work again, as you can see from the archive research paper here. It's again from December of 2015. So it's a late 2015, early 2016 research paper, and most of the authors are from Google. So the first thing that whenever I see a research paper from Google, I expect it to be very high quality, especially in terms of the software optimizations, software or algorithmic optimizations. Because most research papers at Google, especially deep learning papers, have because Google itself has very, very good software engineering or algorithms guys, right? You typically tend to see highly optimized algorithmic code or algorithmic ideas when you look at research papers from Google. For example, if you look at Word2Vec, right? Word2Vec has lots of nice optimization techniques, right? Like negative sampling, Similarly, like hierarchical softmax, right? These are software engineering algorithms techniques to speed up Word2Vec. Similarly, even in the Inception network, you see a very, very interesting algorithmic or a software optimization which speeds up a lot of things, right? This is the original research paper. The original research paper is slightly harder to read, but there's a very nice blog. It's not too hard actually, you can read it. But there is a nice blog that I came across written by Ashutosh Kumar, and I'll provide the reference link to this URL in the description section of this video. And I think some of the graphics in this blog were derived from Andrew Ng's. Andrew Ng is a phenomenal professor at Stanford, has fundamental contributions to deep learning. He has a course at deeplearning.ai. I think I've seen some of these slides in his, and this handwriting also looks like Andrew Ng's handwriting. So I think some of these slides have been borrowed from Andrew Ng's deep learning.ai. So thanks to both Ashutosh who has compiled some of these, and also to Andrew Ng's course, which has some very, very interesting explanation of some of the very interesting and hard concepts in deep learning, right? So let's take the core concept itself, right? Suppose you have a tensor which is 28 by 28 by 192, right? So if you look at any of our models, we either do 3 cross 3 convolution or a 5 cross 5 convolution, or we choose to do a max pool. We can also do a 1 cross 1 convolution, right? So the core concept is every time we are choosing, every time what are we doing? We are choosing one of the kernel sizes. We are choosing a kernel size, and we are choosing whether we should do max pool here or later, right? Instead of doing all of it, why don't we just do kernels of different sizes? Why don't we have a 1 cross 1 kernel, 3 cross 3 kernel, 5 cross 5 kernel, and a max pool kernel, everything at every layer? Why can't we do it, right? So imagine this. So you have a 28 cross 28 cross 192 tensor, 3D tensor here. So if I have, let's assume if I have 1 cross 1 kernels or 1 cross 1 filters, and imagine I have 64 of them, right? So each of my kernels will look like 28 cross 28 cross 192, right? And I have 64 such kernels. So this green area that you notice here, is the output of applying 64 1 cross 1 kernels, right? Because look at the output size. The output size, this is 28 by 28. The output size is also 28 by 28 here, right? This whole green area are the outputs of 1 cross 1 convolutions. And I have 64 such convolutions. So this depth here is 64, or the number of channels here is 64, right? So first I apply 1 cross 1 convolutions and build this whole green 3D tensor. Then I'll apply 3 cross 3 convolution, and I'll use padding equals to same. And let's assume I use 128 such kernels, okay, generating this blue 3D tensor. Look at this blue 3D tensor. It has a depth of 128 as written here. And because we are using same padding, its length and width, right? Its length and width are 28 by 28. Now, because the output of your first 1 cross 1 kernels is 28 cross 28 cross 64, and your 3 cross 3 tensor 3 cross 3 kernel output is 28 cross 28 cross 128, I can stack one on top of the other like this. Like this whole green thing is 1 cross 1 convolutions. This whole blue thing is 3 cross 3 convolutions, and I can stack one on top of the other. because they are of the same size. Look at this, they are the same size. The depth is changing, right? This depth is changing, except that the length and width are the same, right? Similarly, I can do 5 cross 5 convolutions. Imagine if I do 32 5 cross 5 convolutions, and let's assume, of course, I'm using some padding here. Similarly, if I'm doing max pooling here, right, I can also do max pooling with some stride length uh, and my padding being equal to same. And if I'm doing multiple max pools instead of one max pool, here I'm doing 32 max pools here, right? So what I eventually get is this big block or a big 3D tensor. I'm getting this big 3D tensor, which is a combination of applying 64 1 cross 1 filters or 64 1 cross 1 kernels, 128 3 cross 3 kernels, 32 5 cross 5 kernels, and 32 max pools. Of course, I'm having some padding here, some padding here, some padding here. Stride is equal to 1. But eventually the tensor that I'm getting here is 28 by 28 by 256. And how did I get this 256? This 256 is 32 plus 32 plus 128 plus 64. Right? So I'm not compromising on which kernel size to use. I'm not compromising on kernel size. I'm not compromising on whether I should do convolution or I should do max pooling. Because in single layer, I'm doing everything. Right? So now what if, so this is called an inception. We'll come to what inception is. So in the Inception network, what we do is instead of choosing a kernel size and instead of choosing between convolution and max pool, we do everything. Okay, but there is a small catch here. That's where the Google's software engineering optimizations come into play. Imagine, let's take a simple example. Let's take a very simple example. Okay, imagine I have a tensor which is 28 by 28 by 192. So this channel depth is 192. Okay, imagine I'm performing convolution on this with a convolution size of 5 cross 5, right? With some padding equals to same, and I have 32 such kernels. What does my output look like? My output, because I'm using same padding, will be same as this input. This is 28 by 28. So this will also be 28 by 28. What about depth? I have 32 kernels here in this convolution. So this depth will be 32. The big question here is, how many computations do you have to perform? The number of computations. The number of computations you have to perform, right, to eventually get this 3D tensor from this 3D tensor. So this is my input tensor, this is my output tensor, right? This is my input tensor and this is my output tensor. And what is my convolution size? To be precise, my convolution kernel has a length of 5, width of 5, and it has a depth or a channels of 192, because I need to actually have this channel length to be same as the channel length for my kernels, right? For each of my kernels to write it very precisely. So how many computations are needed for this? Let's do a simple calculation. For every pixel here, what are the total number of pixels do we have in this 3D tensor? We have 28 cross 32 numbers, right? We have it's basically a three-dimensional array. So in this 3D tensor, there are 28 by 28 by 32 numbers. For each number, right? For each, to compute each of these cells, how many computations do we have to do? Remember, our convolution has a length of 5, a width of 5, and each convolution has a depth of 192, because this depth is also 192. So to generate one value, you need to take a 5 cross 5 tensor of depth 192 and multiply it with our kernel also, which is this, to generate one value, right? So to generate one value, we need to perform 5 cross 192 multiplications and additions, because you'll take this small tensor here, you'll take this small tensor, which is a 5 cross 192, and you'll multiply this with this 5 cross 192 kernel, right? You'll multiply this, you'll do component wise multiplication and sum them up, right? So how many multiplications and additions do you need? 5 cross 192 to generate one output. And how many such outputs do we have, or how many such numbers do we have in this tensor? 28 cross 28 cross 32. So the total number of calculations that you have to do is 28 cross 32 multiplied by, this is the total number of cells in this tensor, and this is the number of computations that you need to do for each individual convolution. This itself is 120 million multiplications and additions, of course, massive number of additions, Okay, so researchers at Google said if just one simple 5 cross 5 convolution is so expensive, right? Imagine I have to do multiple convolutions. I have to do 1 cross 1 convolution, I have to do 3 cross 3 convolution, I have to do 5 cross 5 convolution, and this is just one layer. In just one layer, I have 120 million computations. That's crazy large number. So they said, can we optimize this? And here is the software engineering innovation. So they said, if this is my input, if this is my input, and this is the output that I'm looking for. Look at it. What is the output that I'm looking for? This is the input that I'm looking for. The output I'm looking for is a 28 cross 28 cross 32 after applying a 5 cross 5 kernels. Kernelization where kernel size is 5 cross 5. So they said, instead of directly going from input to output, if I use a 1 cross 1 kernel as an intermediate kernel, right? So instead of directly going from here to here, remember when we went from here to here, we got 120 million computations that we had to do. So the software engineers at Google said, okay, can we optimize it? So a very beautiful hack that they realized was, if I perform a 1D kernel first, a 1 cross 1 kernel first, right, with 16 such kernels, right? So what does each of my kernel look like? Each of my kernel is 1 cross 1 cross 192. And now if I perform a 5 cross 5 kernelization on top of it with 32 kernels, the result that I get is very similar to the result that I get here. The result that I get here and the result I get here is the same. But the advantage here is, now when I do the computation of on the number of computations that I need, the total number of calculations that I need now are, look at this, how many outputs are here? 28, 28, 16. What is the size of each kernel? How many numbers do we need to compute in each kernel? 1 cross 1 cross 192. So this whole thing will finish this convolution. What about the second layer? In the second layer, the output we are expecting is 28 cross 32. And each of my convolutions are 5 cross 5 cross 16. Okay, and I sum up these two, because after this happens, I'm doing this. Right? Now my total number of computations is 12.4 million computations. So I went from 120 million computations to 12.4 million computations using the 1 cross 1 kernelization trick. This is also called as a bottleneck layer. This is also called the bottleneck layer because this is much smaller. This is large, but this is small. That's why it's called a bottleneck. Right? And this is a very nice software engineering hack. So the Inception module that they've realized should look like this, okay? So the way they do it is this. So suppose I have the output from the previous stage, which are called previous activations. These are the outputs from the previous stages. And I have the next stages here, okay? Whatever is the output that I get from previous stages, I will perform a 1 cross 1 convolution and create all the values here. Then I perform 3 cross 3 convolution via 1 cross 1 convolution, the way through the bottleneck layer, as we have seen just a while ago, that this is much more optimal in terms of number of computations than just doing a 3 cross 3 convolution. And then I do a 1 cross 1 convolution followed by a 5 cross 5 convolution. See, this will generate some values, this will generate some values, this will generate some values. Then again I perform max pooling with 1 cross 1 convolution. All the outputs that I get here, I'm doing a channel concatenation. What is a channel concatenation? The outputs are all the same. Look at it. The output length and width are the same. The channel sizes change. So this is what it means by channel concatenation. The output that I get here becomes the input to the next layer. This cool idea is called the Inception module, right? Where I'm taking the outputs from the previous stage and to generate inputs to the next stage. So I get a 3D tensor here and I output a 3D tensor. In between, I'm doing a 1 cross 1 convolution, a 3 cross 3 convolution, 5 cross 5 convolution, and max pooling, all of them, and then I'm concatenating the results, just like the way we have seen earlier. Right? This is what we want to achieve. But doing it directly is very expensive. That's why we are doing it via a 1 cross 1 convolution. This module is called the Inception module. Right? This is a brilliant, when I first read this paper, I said, wow, I think I read this paper somewhere in early 2016, right? When I read this paper, I said, wow, this is beautiful. Because look at this, I really love this algorithmic optimization of trying to achieve 3 cross 3 convolution, 5 cross 5 convolution, using one cross one convolution in between, right? So the actual Google net, the actual Google's Inception net, which is also sometimes referred to as Google net, and it's a homage, or it's in respect to Jan LeCun's LayNet, right? This is a 1998 net. So Google named their network Inception Network or Google. So instead of calling it Google Net, they kept the L capital here to respect Jan LeCun, who built one of the first very successful deep neural networks. And the actual network looks like this. This is how the actual network looks, with lots of layers. The red ones here, look at this. This is your inception module, right? This is your inception module. This is your inception module, right? So you notice lots of inception modules here, right? And of course, you have the regular ones. All the blue ones are convolutions. The red ones here are your max pools. This is basically concatenation of channels. Okay, it's a very, very deep network. It has a lot of depth here. If you notice, it has a lot of depth, but you'll notice this type of structure. Look at this. You'll notice this type of nice structure. The inception module, you notice it at a lot of places, right? So look at this part. Okay, you'll see a lot of this inception type of architecture all over this network. It's a fairly complex and deep network, frankly, right? But it works phenomenally well. And the Inception network, just like everything else, has multiple versions. And here is an implementation of the Inception network in Keras. This implementation is non-trivial, unlike your other networks like VGG, because look at it, the network itself is fairly large. The network itself is fairly large, but the Inception module is not very hard to understand, right? So you have Inception module, and look at this whole network. You have convolutions, you have max pools, and then you have these branches. Because you keep seeing these branches, right? Because this can be thought of as one branch. This is another branch. This is another branch. This is a fourth branch. So that's how the code is written in Keras. So if you really want to understand the Inception module, I recommend you to spend a couple of hours going through each of these lines of code and connecting the dots between this code. It's not very hard, frankly speaking. I've done it only once myself. It took me a couple of hours to digest this whole code when I first read it, right? So go through this code and connect the dots between that and this whole diagram, right? This whole diagram. So you can actually get a full-size image also here. So let me just click it for you, right? So this is the full-sized image. So my recommendation for you is, because you know all the building blocks, right? You know all the building blocks. So what you can do here is you can go to Keras and look through each of these codes. What all you have is basically convolution followed by batch normalization. So there is conv2D followed by Bn. So there is actually layer which is represented here, which is basically apply convolution plus batch normalization. That's defined here. And what we're building right now is basically a bunch of conv2D and batch normalizations with max pooling and some branching. So you'll have to go through this code very, very carefully while keeping this picture in mind, right? Then you'll understand it. It took me a couple of hours when I first did it, but it's doable, trust me.